Once next speaker is Huaizhong Zhao, and he's going to talk about the periodic solutions of SPD.
First, I'd like to thank the organizers very much for the kind of invitation to give me opportunity to talk here. So I talk about random periodic solutions of SPDEs. So I like to start from well-known things to set this up. So this is my the driving flow I have is, so first this is for the noise, it's driving noise, and you have start from probability space, and then you have theta. Theta is a measurable flow on omega. It's a map from omega to omega, and such that theta is measurable, and theta 0 is identity map, and also satisfy this group property theta s compose theta t, theta s plus t for all s and t in R, and also this is P preserving measurable flow, and this is well known. I don't want to spend time on this, and this is definition of random dynamic system, and this random dynamic system basically is a map. Okay, it's map. This is time. Okay, maybe different, but here for my interest. For this talk, I consider the real line from minus infinity to plus infinity. So this is phi is a mapping from this is time, this is the sample space, and this is the state space, and this is a map from this to x. So you have this t omega and x, and mapping to phi t omega x with following properties. Okay, so the property we have is first is a measurability, and phi must be measurable, okay, and also satisfy this Kusager property. The Kusager property, first one is when t is 0, and this is identity, and also phi. If you start from time 0 and you go time t plus s, first you can go to times s, and then and then you go time t, but you start from this from this omega at this time s, called this theta s omega. We just set this up. So that's a definition of a random dynamic system, because I considering periodic solutions, and periodic solution is a kind of invariant set of random dynamic system. And so to go back to link this to SDE, it is quite natural. It's very natural to regard SDE and SPDs as random dynamic system. There are a lot of experts in this room of this topic. So actually, the idea went back a long time ago, maybe late 70s, with the work Elvaze, Kuninta, and Arnold, and other people on SDEs. So the idea is very is the following. The idea is you have this SDE or SPDE. Let's talk about this SDE first. So this is the SDE, and this is initial condition, and you solve it. And you have suppose you can solve it. You have unique solution, and then we can regard this as a map, okay, as a random map, and because x can be any point in H, and then you think this is the map from H to H, and this is for this SDE, and this shift is driving a metric dynamic system we consider. So theta t omega at theta t omega at time s is just a shift Brownian motion. Okay, you shift as you cut it at time t, and you move back to the origin. And also another crucial idea is that you because this is the autonomous case, and actually you can start from a time s, and with this initial condition, and then you have the following property. Okay, you have that actually start from s, you arrive at time t plus s, and actually just like you start from 0 and you arrive at time t, but with different realization. Okay, with this shift Brownian motion, and with this observation, you can see the following immediately. You can see that you can see this. If you start from 0 time 0 at time x, and to arrive at t plus s, time t plus s it's like you start from 0 to s, 0 to time s, and then from s to s plus t. T plus s plus t, And but this, with this property, it's just like, here you start from 0, but at after time t, but you start from this different realization. You have the following, and translate to this, you have this cosine, well, not really cosine yet, because this, you take away this measure set. This measure set might depend on s and t and x. And the next thing is to use the perfection to make this co-cycle. Okay, actually, to make the the perfection process to make cosine is a very difficult thing. And this this well-known people consider this like deformism, this stochastic flows, and then you can perfect this. So at least some references. They are well known. This is for SDE and this is for SPDEs. So this is not the main thing I like to talk. So I go quite quickly on this. So this is a slide I like to draw attention that I compare this SDE and SPDE and also ODE and PDE, and then compare this deterministic dynamic system and also stochastic dynamic system. Okay, so it is well known that ODE and PD generate dynamic system, and also SD and SPD generate, in the case that the reference I gave, generate stochastic dynamic system. Okay, of course, this relation, there are a lot of work on this, and there are still some open problem on this. But let's talk about the other things. Dynamic system people are interested in long-term behavior. Okay, and to study long-term behavior, the one of the thing is very important thing is consider the equilibrium point. Okay, there are two. There are many kinds, but there are two basic kinds. One is called fixed point. One is called periodic solution. Okay, so if you're on this line on the stochastic case, and we need also similar thing. So correspond to the fixed point, and we consider random stationary solution, or called random fixed point. And in fact, it's not really fixed point. It's moving. It's moving kind of stationary solution. So and also, so the question asked is, do we have some kind of periodic solution, random periodic solution corresponding to the deterministic periodic solution? Also, I like to mention that, in fact, there are a lot of work on invariant manifold, and in invariant manifold there is a basic assumption. A basic assumption is there exists either a fixed point or random fixed point, or there exists attractor, and it seems to me very interesting to study whether or not this kind of thing really exists for SD or SPDs. So today I concentrate talking about stochastic random periodic solutions. So I like to mention this motivating problem. So I have this stochastic or maybe SPDs if this is a second order differential operator. So I have this equation. Okay, this is stochastic different equation. So one question physicists or dynamicity people to ask is the following: suppose this term disappears. Okay, suppose the noise term disappears. Suppose this equation, so the noiseless equation, which is dx is equal to ax plus bx dt, or dt here. This has a deterministic periodic solution, which means with period tau, it means you have a solution that zt plus tau is equal to zt for all t. Suppose you have the following. One question to ask is do you have a you go back to this equation, okay? What kind of thing can you say? Do you expect you have some kind of periodic solution, or you kind of other kind of period? This is the definition of deterministic periodic solution. Okay, so this is the period, of course, zt plus tau is zt, and also phi tau zt is equal to z plus t plus tau. And the answer definitely you can imagine that the answer should be no if we think the periodic solution in the random case is in the sense of the deterministic sense. Okay, it's just like stationary solution or random fixed point. Fixed point is not really random fixed point is not really the fixed point in the deterministic sense. So I like to start from this example. This is computable example, and you can compute by hands. And this is this is a two-dimensional ordinary differential equation. Okay, and this appears in any probably elementary ODE course. And in fact, for this equation, this x squared plus y squared is equal to 1. This is a limit cycle. Okay, basically is a circle, and it's a periodic solution. So I have and then I add this noise. This is a simple form of kind of noise, and the reason I added this is computable. Okay, and in fact, what we understand now is a lot more than that. We don't need this kind of restriction at all. But let's consider this. And in fact, if you define rho star, this way, the form we get this is the following. We use the polar coordinates, and we transform this to polar coordinates. We transform to the radius and also to the angle. The radius actually satisfy equation which is dr is equal to r times 1 minus r squared dt plus r dwt, and that equation actually, the stationary solution is solvable, and that formula rho star can be found in the book of Arnold. Okay, that's for the stationary case. But I use this to construct this periodic solution. Okay, so this rho star omega multiplied by cos 2 pi alpha, which is the rotation of this thing, and this rho star omega sine 2 pi alpha plus t, and then one can check the following. One can check this is periodic. It's very easy to check. And also one can check if you start from phi omega 0, and this is phi theta t omega. Okay, and it's like this is some kind of periodic solution. And in fact, you can prove the following as well. You can prove you start from any initial condition x0, y0. If this point is not 0, and then you pull back. Okay, you pull this solution back, and to minus t, and then you go forward to time t, and you consider x squared t plus y squared t to pull back at theta minus t and theta minus t, and actually this converges to this rho star omega squared. This suggests this is very similar to the deterministic deterministic sense. If you this is it's like you have limit cycle, stable limit cycle. You start from somewhere, and then when time goes to 0, goes to infinity, and x squared t plus y squared t converges to this number here. And this definition, so we started actually we were motivated by this example is computable and it's easy to understand, and so this definition I gave with my paper with Zheng from Chinese Academy of Science. That time I defined this random periodic solution is this phi. Phi is a map from is random. It's a random process, and satisfying the following: phi omega s plus tau phi omega s. Phi omega s plus tau is phi omega s. That's right, yeah. And this relation omega, and then if you run this, and you run this to this phi theta t omega, okay, and this is start from s, and then after time t you at this phi t plus s, but you at this different realization. And I will show you a movie, and this movie you can see clearly what this phi is. But before I'm doing this, I like to rewrite what we just defined. So what we defined was phi omega s plus tau is phi omega s. Okay, but I like to write this as following form. I like to write phi theta s plus tau, and then theta minus s plus tau. If I have this two-sided time, and s plus tau, and you write it like this, you write that. Okay, you think I do nothing because it's really doing nothing. It's just rewrite this to motivate to the following line. So and then you can see I write to I think this is my omega. If I think this is my omega, and then you can have this phi theta s plus tau omega s plus tau is equal to you have to change this omega as well to change to phi theta s theta tau omega s. Okay, and then you do the similar thing for this. You regard theta minus s omega as omega for this one, and you have the following. You have this phi t theta s omega, phi theta s omega s equal to this. But then you set it following. I think it's phi t theta tau omega, theta t omega. I write this as y t omega, and then I derive the following. Okay, I derive actually what we think here is this y, tau plus s satisfy the following. Satisfying the y tau plus s omega is y s theta tau omega. Okay, it's nearly periodic. It's not periodic. Okay, but if this is deterministic, you can see this is periodic. Okay, but it's periodic in the sense that y tau plus s omega is ys, but at different realization set theta tau omega. Okay, and also if you think this is also a solution, you can see the following. You can see ys omega. If you run this map, you run this point by this map, phi t, but as realization theta s omega, you arrive at it as y t plus s omega. It really is a solution. So next, so I like to what did I do? I have to get this radio. So this is my the simulation. Actually, the equation I showed you, this computable example. So you can see this is this actually is a lot of circles. This is my phi. There's this lot of circles, and you can see this. You start from there. You're moving. This is my y actually. This is my y. This is my y. Okay, you can see this is really a solution, but this solution actually follows the circle. Okay, the circle is my phi. This is a random periodic solution. Follow this circle. You see, you follow here. This also follows this circle, and this is really the random periodic solution I can see. Sorry, maybe we give up, and got the idea already. So go back to. Where are we? Okay. So that's the video I showed, and you can see. I'd like to give her some remarks. You can see actually there are. You see, if you look at this example. This example you have is first, this noiseless system. You have a periodic solution. Periodic solution like this drive the system, rotate. Okay, and then you have noise as well. Actually the noise. What does noise do? The noise makes the solution spreading. Okay, it's like this. This is why you can see the picture. First, in one sense it is rotate. This solution rotate, and in another sense. Actually, it's spreading. It It's not really a circle, but it's follows this circle, and you can see this interaction between the nonlinearity, which give you the periodic solution, and also the noise. Noise makes the things spreading. There are only few light touch to the random periodicity in the literature. So Shozo has a paper on, and also thesis. David showed me, remind me this result, and on the random periodic distribution. And later there are some other works, this Stochastic, Michalik, and Kloner, and they consider random periodic distribution. And this paper is not. This is the random mapping. Okay, so I like to link the definition I just gave, and also periodic distributions. Probably a lot of people are interested in this. So what is this? So the thing we can see is the following. The thing we can see first is random periodic solution I just gave would give you a random would give you a periodic distribution. So the setup is following. The setup is we consider this skew product measurable space. Okay, this omega cross x. This is the well-known thing, and also this is the well-known. Okay, this is the metric dynamic system, and we because you regard this. So this is a skewed product system theta t omega bar, which is theta t phi t omega x, and this is my omega. Okay, omega bar. This is omega x, and then this is the random dynamic system on this metric dynamic system. On this metric dynamic system, omega phi bar t omega bar x is phi t omega x, and then I define the following. I define for any a not in f. Sorry, it's not. It should be in f bar. Okay, sorry. For any a in f bar, and then let a omega be the omega section of a in the space x, and then we set the following: mu as a, which is a measure on this defined on this f bar, not f. Okay, and this is direct delta measure y as omega, and acting the set is a theta s omega. You define the omega section, and this is the theta s omega section, and then dp, and you calculate the expectation. And then the recent result we got is you can prove the following. You can prove actually this measure you define here is periodic. So mu tau plus s is mu s, and also this map, this we just defined this metric dynamic system. Actually, if you're acting on mu s, this is equal to mu t plus s. This is for any t. And similar to the relation between station solutions and invariant measures, and actually the existence of a periodic measure we just seen here does not imply the existence of random periodic solution in general. But this can be true over if you consider even a larger, enlarged probability space. Okay, so this is the converse part of that result. So if you set I be this interval 0 to tau, this is the one period, and I consider this trivial sigma field. I call this Bi, and then this is my probability sample space omega, new probability space I times omega cross x, and this is my omega hat, and this is my new theta. I call this theta hat. This is the triple ones. Okay, this I cross omega cross x1. This theta hat t omega hat is first. I have this s plus t. I mod this tau, and then bring back this interval I, and the second one is theta t. Third one is phi t omega x. Okay, and this is the random random dynamic system on this new enlarged probability space, And then you define mu as following. For A in phi, this is phi bar, so F bar, sorry. And mu, if on this set here, and is equal to the integral of mu as a ds, okay? And then divided by tau, this gives you the probability measure. And if this amplitude set is 0. And then for if omega hat is like this, okay, as omega star, x star omega star, if this is in omega bar, I set this yt omega hat bar is equal to phi t plus s theta minus s omega star and x star theta minus s omega star. And then you can prove the following. You can prove this measure mu hat is a probability measure, okay, on this enlarged probability space, and also this theta hat t is measure mu preserving, okay. Theta hat t actually mu is equal to mu. And it also satisfies the following. This theta hat t1, hat t2 is equal to theta hat t1 plus t2. And also this phi bar, actually, phi height, sorry, is a random dynamic system on this enlarged probability space. And this has a periodic solution y hat t omega bar. This is what I defined there. So, in fact, this gives you two-side things. If you have a random periodic solution, and you have a periodic measure, and then if you have periodic measure, and you can construct a enlarged probability space, and you get a periodic random periodic solution. But this this is to me this not result. On the other hand, this is not really what we are interested, because by doing this we change the whole problem to a different problem. The different problem is you have different probability space. So what we're really interested is to study random periodic solution on the original probability space. Okay, so let's coming back to the problem. This is a perturbation problem. Okay, so I have this SDE, and if I assume the noiseless system has a periodic solution, and what can we see about the original SDE? And so that is the solution, is the periodic solution of the noiseless system. I do this kind of transformation. Okay, this is the standard transformation. Okay, but if I do this transformation, suppose X is our solution of the original equation, and I then transform this problem to a problem for U, and I can write down the solution, equation for U, and this is the equation for U. You can write down what this F and B0 are according to the original solution equation, and in fact, this equation, this F and B0, they are deterministic functions, and but they're also periodic in T. Okay, periodic in this T. Okay, the periodicity actually is from the original periodic solution of the noiseless system, and so in general, in fact, we can discuss this problem. Okay, we can consider this equation. Okay, normally I set this as RD, and then I move on to SPDEs, and satisfy this condition. Okay, this is periodic. For simplicity, I first only consider additive noise. Even in the case of additive noise, there are a lot of difficulties, and for the multiplicative noise, you need some other techniques like anticipating integral, things like this. And so actually, what we studied there is SDE or SPD with time-independent coefficient. Actually, this doesn't give you a co-cycle, but it may give you a kind of a semi-flow. Okay, for the semi-flow, this is our definition of a periodic solution, a random periodic solution. So this is where is my periodic solution. So you don't have this shift anymore, but you consider this y as omega, and you're starting from S, and you run another time, to the time t plus s, actually run time t, and you get yt plus s omega. And also this is similar as before. This is periodic. This is kind of random periodic. And the tool we use is stochastic integral equations. So because I'm interested in not only stable case, you use pullback. It's in stable case, it might work. But I'm interested in a non-dissipative case. You have some direction, you might have might be contracting, and some direction might be expanding. And so you can see. So what I do is I decompose this RD to two subspaces. Okay, one is ES, one is EU. ES actually spanned by these eigenvectors correspond to the eigenvalues with negative real part of A. Okay, so maybe this should be plus, I think. Yeah, sorry. And EU actually spanned by these eigenvectors of eigenvalues corresponding to the positive real eigenvalues. And so mu m is actually the largest negative real part of eigenvalues of A with largest negative real part, and mu is the smallest positive real part. And then you can decompose this, and this is my W, and B0 also I suppose this is bounded, and this is a well-known formula. Okay, very constant formula, and so I learned this from my for the ODE cases from ODE course, and then later on from Dr. Zabjek's book from for this for the stochastic case. And then I decompose this, and that can define the projection. P plus is the projection from RD to ES. ES represents negative eigenvalue path, and P plus represents positive eigenvalue path. This is unstable part, and this is stable part. And then you have this decomposition, and then this is my the integral equation I use to solve this problem. Okay, the integral equation. Actually, you can see this integral equation is infinite horizon. Okay, from minus infinity to plus infinity. Okay, minus infinity is like the idea of the pullback. Okay, because this corresponds to the negative eigenvalues, and plus infinity like you can't pull back, pull forward probably from future infinite direction, and this because this corresponds to the negative positive eigenvalues of positive real part, and this way you make this thing this integral convergent. Okay, actually these are the because these are in dimension or in SPD case these are infinite dimensions that are coupled by this equation from positive from these two directions. And so the first result we proved with in this paper with Feng and Zhou, and is following. If you can solve, it means you can this coupled forward backward infinite horizon SIE has one solution. Okay, if and only if the solution satisfies the following. Okay, it means if this has one solution, it must be a random periodic solution. Also, if it's a random periodic solution, and with little some assumption like tempered, okay, it's a very minor assumption, and then you can prove this. If we satisfy this, actually will satisfy equation 17, this stochastic integral equation. And it seems to us, this provide another analytic method studying periodic solutions, which is different from Poincare geometric method in the deterministic case. Actually, in the Poincare geometric method, you study the map, you study the fixed point, but because in the stochastic case, you start from somewhere and it doesn't come back. Okay, it doesn't have a fixed point. So so the method is not easy to use. the solution has a unique solution. Okay, this is just a equivalent condition. Okay, I haven't said the equation has a solution yet. Okay, this would be next theorem. Okay, I only make the connection between the random periodic solution and the solution of this equation.
Do you not have the condition that somehow that the flow keeps the measure varying?
For us, it's automatic because I consider the Brownian motion case. I also consider this theta, as a shift. Okay. I do have. It's kind of given in my problem.
Brownian motion itself in yours?
Yeah. In my case, I consider this equation. Okay, this SD with this additive noise, and also later on I consider SPD with additive noise, and the theta is a shift. Okay. So in order to solve this, in order to solve this, I need to put some more conditions. So this is so f is really my nonlinearity. Okay, so I assume f is continuous. Okay, and globally bounded, and this equation, this condition, probably you're really looking for. This this is also Lippius. Okay, I assume a little bit more strong condition. I like this Jacobian grad f to be globally bounded, because I need to calculate the Malleman derivative, and this condition, and also you need this b is a Holder continuous, and then you can solve this equation. Okay, you can solve this equation, and in fact, this condition f, okay, is globally bounded. At the very beginning, we thought is some kind of condition is not very good. In fact, this is quite natural condition. You cannot simply make this Lippius. So because you remember in our equation, I have this AU part, I have this F part. F is my nonlinear part, and AU is capture my linear part. So you cannot just change this some part of A to F, and because I have the two-sided. This two-sided equation, and relax this condition. On the other hand, this condition might be relaxed by some actual technique. It's not this kind of technique comparisons like this. So this is my SPD case. Okay, my SPD case, I consider this du is this divergence form operator, or second order operator, plus FTU, and this is I consider this additive noise. Okay, this is my additive noise, and this is my initial condition. Okay, and with this, so my D here, for simplicity, I consider a bounded domain with smooth boundary. So to relax this is not really, my emphasis at the moment. So so with this directly a boundary condition, and with this you have. We also assume this is a uniform elliptic. Okay, Aij cos I cos j is bigger than or equal to gamma cos norm of cos squared, and is symmetric. And this you can have these eigenvalues mu k, and also this grad phi k. These eigenfunctions. Okay, the eigenfunctions phi k. They satisfy this equation. And further, we assume this sigma k squared less than sigma k squared less than infinity. And this is the Euro assumption. And then you can decompose this L2D to ES. ES, this corresponds to eigenvalues of with negative negative real part, and EU corresponds to positive real part, and this is the finite dimension, and this is infinite dimension, and this is my hit kernel. Okay, and it's important for me because we need to calculate the derivatives, things like this, and so this is normal various constant formula method, and with this, and I write down this equation. In my inspiration, I try to solve. Okay, similar to the SD case. This is something I try to solve, and indeed I can prove if this unique initial value problem, if the initial boundary value problem has a unique solution, and then you can solve, if you can solve this equation, and the solution of this, actually is random periodic. Okay, so how do we solve this equation? Okay, I denote this by y1, and this is the solution. This is the space we try to solve. This is C in L2 omega cross D. D is my domain, and omega is my probability sample space, and that's the time. Okay, so the time I have is from minus infinity to plus infinity, and this is the continuous function from time to this L2 space, and also satisfy this periodic condition. Okay, so what I try to do is I try to solve this equation. I lift my solution to this space. I try to solve this equation on this space, and of course, so the equation is, if you do some kind of transformation, simple transformation, and you can make this to a random equation. Okay, that's random equation we have. Even this random equation is not easy to solve it, and of course you can put a very strong condition, and for example you can use Banach fixed point theorem, but this really have very strong condition on that, and so that's the equation we try to solve. If we can solve this and then use our theorem, and you can see the solution of this z maybe plus is y1 give you a solution, random periodic solution. And to solve this, this is the mapping. Okay, so this is my map M, curly M Z for Z in this space. Okay, and this MZ which is the integral. Okay, this infinite horizon integral, and so the question is whether or not we can find a fixed point of this map in this space. This is space we try to solve this equation. This is not omega was space, and we solve this equation in this L2 omega cross D. The fixed point theorem we use is Schroeder fixed point theorem. We have slight modification, but this basically is the Schroeder fixed point theorem we try to use. And in the Schroeder fixed point theorem, and the crucial thing is to check the relative compactness of a certain subset. And this is the relative compactness theorem we use. And so I go through this. And actually this went back long to let maybe give you the reference first. This for the L2 version, go back to Professor Plato, Malevin, and Newlat, and this paper in 1992, and also Peasant in the Polish Academy, and 1993. This is in L2 space. Okay, so you have compactness in the L2 space, and but later this nice paper by Bali and Sasuria, and what they made this, they consider this compactness in this space L2 0T L2 omega cross D. Okay, and everything L2, and what they need is they consider everything, kind of Malevin derivative, and consider everything in the L2 space. So, but this is not quite enough for us. Okay, of course, L2 space, the result itself is not enough because we have, we have space, we have time. Some is there. So, but what we need, this L2 time is not enough for us. And what we need actually is for the time we need this is okay. R2 omega for this is okay for us, but for time we really need a continuous space in the supernorm of time. And this is the based on this kind of result, this is what the result we use. So what you need is we consider this sequence Vn in this space, okay, C0, 0t L2 omega cross D, and of course because it's, in order to get relative compactness, you need the boundedness in this space is not enough, and you need certain other kind of other conditions, and of course if it is well known that if without this probability without this, and only R2D, you may consider the stability of H1 norm to be bounded. That will be enough. But you have this probability space, and so first condition you need is this H1D norm, an expectation of that, and this is uniformly bounded. Okay, and also we consider this Malevin derivative. Okay, this Vn Tx, and it's a Malevin derivative, and you integrate it in with respect to this space here, and there's already integration here already, and you take supreme norm on time and also on n. This is the finite, and also you need more. You need some kind of equal continuity condition, and the Vn here. So we need Vn T1x minus Vn T2x. You compare T1, T2, and you integrate. You take the expectation and you integrate out, on the space D, and this is less than C T1 minus T2, give you some kind of equal continuity. And also you need the following. You need this. The Malevin derivative actually is uniformly continuous in this T, and also in this theta as well. And this is that condition. And also it's on the boundary. On the boundary is you can control as small as you like. And then with this kind of condition, and then this Vn is relatively compact in this space. And this really what we need, because with this you can consider one period, and one period is compact, and because some kind of periodicity, and you can make this to the whole space, and then you get the relative compactness of of larger infinite times space here, and so this can be used to do our job, and to solve this infinite horizon stochastic integral equation, and when you solve this, we can see this. You have a random periodic solution. Okay, thank you very much.
Thank you very much. Are there any questions or comments?
So concerning this infinite horizon stochastic integral equation, so the solution is no longer adapted to anything, right?
That's right.
So is it of any use then? Because you cannot apply any stochastic calculus to this anymore.
Well, this is the nature of the problem, because they are
right. Well, you circumvent the problem.
Yes.
You have two different classes. Of
that's right. Yeah. Is any use? Well, you could make it. Maybe it makes sense by considering this is the link with the work of Newland and some other people on the actually you have this SDE or SPD with anticipating initial condition.
Yes.
And you can I think Tushen also has a paper with Salam Muhammad to consider SD or SPD with anticipating, because it's really if you look at this the problem here is really that this kind of link is very strong, because really
but you are aiming at a representation of a solution of an SDE or
yeah.
But this representation is no longer, let's say, adapted, right?
the representation is no longer adapted. But if you in a stable case, if you have one direction, for example,
Right, that's clear.
It's still clear. Yeah. But this is the nature of the problem.
Any more questions, comments?
Just, a simple question. When you look at this case, this semilinear case,
Yes.
what happens in your case if you have, for the linear problem, negative eigenvalue?
Linear case.
Yeah, the linear part has a negative eigenvalue, and the other conditions are the same. Then what do you get?
I think in that case, you in the condition I said, because I consider this F to be bounded, okay, and globally elliptic. With this condition, you only have one side. You only have one side if all the eigenvalues are have not negative part. Yeah. Yeah. But for if I coming back to quite really to your problem, if I come back to the original problem, the perturbation problem I have, okay, it means the original problem I have this. You have this limit cycle random periodic solution. I perturbate. So the condition I put maybe is to be bounded. Okay. So simply I can cut the system, Stochastic system, with a large ball. Okay, and the dynamics, as far as this periodic solution is concerned, the dynamics of the deterministic system is the same. Okay, as far as this is concerned, and then you perturbate, and you have random periodic solution. I think what we could do is we could do a lot more, by working harder, considering comparison theory, without this kind of condition. But it's not simple. It's not simply to change this boundedness to a Lipschitz condition. It seems to me.
Because the deterministic. Then I couldn't follow this where you were constructing this intersection of the station of the stable and the unstable manifold.
Yeah.
It's basically kind of what you lifted to the stochastic case. But I didn't see where kind of the you avoided this kind of running away to infinity, which you have in the stochastic equation always. If you have one eventually.
You need the solution running away to infinity.
Right.
Yeah, that's right. Yeah, with this bounded condition on F, you can avoid that. Exactly. We need our solution somehow bounded.
Any more questions or comments? If I see this correctly, to prove this tightness of the measures at the end of the space C0T with values in L2 omega cross D. The problem is because our Taylor's theorem is not so easy to check there, because for every fixed time T you have to look at all your values of your paths, and this you have to prove to be compact in L2 omega cross D. Yeah, because our zeta, the boundedness is not enough if the space of paths is in an infinite dimensional space.
Yeah.
So probably that's why your compactness criteria are so complicated. What you have to show is so complicated.
Yeah, exactly. Yeah, that's right. Yeah.
Because if you only have boundedness is much easier.
Yeah, normally as Zeta is if the value takes in one dimension.
Yes.
But as far as is, the image is compact.
For every fixed T.
Yeah, for any fixed T. Exactly. Yeah. This is why it's complicated, but it's quite useful.
Okay, if there's no more questions, then thank you very much again.